In the previous lectures, we used two intuitive approaches to find the limit of a function using numerical and graphical approaches. With this method, we made a bold claim about the limit of a function. But how sure are we that the function really behaves the way we think it does? Is it really the number L that the function is approaching? What if it is another number nearby? Or maybe the function is not approaching any number at all. Is that even possible? Aren't our eyes just tricking us? No matter how strong we feel about our answer, if it is done using these intuitive approaches, there is always a persistent question: really? The lack of confidence in the answer when these intuitive approaches are used prompted us to take the quest of finding the limit of a function to another level, one that requires a mathematical way of saying that indeed f of x approaches the limit L as x approaches 0. The only way to satisfy the doubters is to respond to the question using the mathematical definition of limit. This is the only way we can say that, yes, I am sure, beyond reasonable doubt. So, are you ready for today's video? Let's go! Formal definition of limit of a function. Let f be defined on an open interval containing c, except possibly at c, and let L be a real number. The statement, this one, which is read as the limit of f of x as x approaches c equals L, means that for every epsilon greater than 0, there exists delta greater than 0, such that if x, the absolute value of x minus c, is in between 0 and delta, then the absolute value of f of x minus L is less than epsilon. Looks scary, right? Well, probably because of the heavy notations. But let us try to understand these symbols first. Epsilon greater than 0 means that epsilon is a real number and is chosen to be positive. Likewise, delta greater than 0 means that delta is another number chosen to be positive. In terms of absolute value of x minus c, it only symbolizes the distance of x from c. Therefore, 0 less than the absolute value of x minus c less than delta means that the distance from x to c is positive but less than delta. Likewise, the absolute value of f of x minus L less than epsilon means that the distance from f of x to L is less than epsilon. It can be 0, but it should be smaller than epsilon.
How does this definition imply that f of x approaches L as close as desired, when x is made sufficiently close to c?
Great question. In terms of, The distance from f of x to L is restricted by epsilon, that one. Because epsilon can be any positive real number, its value can be as small as desired. In effect, the f of x must also approach L as close as dictated by epsilon. The role of delta is to keep up with this epsilon requirement by providing a domain or set of values that the function can take. To better understand this situation, we can think of it as an argument between two people. One is trying to convince the other that the limit of the function is really equal to L. The doubter would challenge the convincer by supplying a value for epsilon. The epsilon whose purpose is to restrict the distance of f of x to L. As a response, the convincer will have to come up with the corresponding delta value that will, in effect, frame the values that x can take. Now, if the distance from f of x to L remain smaller than the given epsilon for all values or for all the values that satisfy the delta restrictions, then the doubter will have to look for another epsilon value, smaller of course, from which the convincer will try to adjust its delta response. If the convincer is always able to come up with a delta value that satisfies the epsilon requirement, then the doubter has to admit that really the limit of f of x as x approaches c is L. But if at least one epsilon is found so that no delta can be supplied that will maintain the epsilon requirement, then we say that the limit of f of x is not L or is not equal to N.
But how can you possibly exhaust all values for epsilon?
The answer is by making epsilon arbitrary. Let me show you how. Let us take a very simple example of limit to illustrate this procedure. Show that the limit of 3 as x approaches 2 is equal to 3. First things first, identify what is what. We need to identify what is f of x, what is c, and L. And there is these values. F of x is 3, c is 2, L is 3. For a positive real number epsilon, we want to find delta such that if the absolute value of x minus 2 is positive but less than delta, then the absolute value of f of x minus L, which is 3 minus 3, is less than epsilon. So we want to find that delta that will satisfy this conditional statement for that chosen epsilon. In all cases, this is this part really that we need to satisfy. And this part can be simplified into if the absolute value of x minus 2 is in between delta and 0, then epsilon should be greater than 0 because 3 minus 3 is 0. Now, are you sensing something? This conditional statement wants to find delta so that this part is met. But epsilon is positive, and so this thing is always true no matter the value delta can take. Therefore, we can proceed by saying that take any delta value, then the above condition is satisfied. Or for the sake of showing a delta value, we could say by taking delta equals 1, the above condition is satisfied. Therefore, the limit of 3 as x approaches 2 is nothing but 3. So that is how we justify. That is for a very simple function, a constant function. So we have found delta. Actually, any delta will do since this is always true. But we will discuss a function where this is kind of demanding and will make us work in finding the value of delta. Let us see. So last time we employed numerical approach to find the limit of 2x plus 1 as x approaches 1, and we saw that it is equal to 3. This is now the time to bring conviction to that claim. Is it really equal to 3? For this problem, f of x equals 2x plus 1, c equals 1, and L equals 3. So let epsilon be greater than 0. That is how we always start. We introduce the epsilon. We want to find delta such that if the absolute value of x minus 1 is in between 0 and delta, then the absolute value of 2x plus 1, the f of x, minus 3, the L, is less than epsilon. The conclusion part can be simplified into this part, can be simplified into 2x minus 2, and then we can factor out 2. Now, focus on this last expression, this one. This is what we want to satisfy. Notice that unlike before, that's our example before, the conclusion part in this conditional statement is not outright met, unlike this one. We no longer have the luxury of nominating a fixed value for delta. This is because for a small enough value of epsilon, this conditional statement may not be satisfied if x is not properly restricted by delta. Remember that epsilon can be as small as desired. So, how can we get around with this changing value of epsilon? Yes, by defining delta in terms of epsilon. In turn, delta will also change as epsilon change. But what value of delta is specifically? Well, take a look. If we want this expression to be less than epsilon, then we would want this, the absolute value of x minus 1, to be less than epsilon over 2, right? This means that delta can be defined as epsilon over 2. And that's it. We've found the right choice for delta that works for any choice of epsilon. If you wish, we can still formalize the justification that we did here into a formal proof like this one. Okay, so notice that this kind of justification requires us that we already know the epsilon when rather the delta when epsilon is introduced. So usually that is not true. That is not the case because we still need to do some work before we can find the delta. But yeah, this is how you do the formal proof. So here I use GeoGebra to visualize what is happening when proving the limit. So this is the graph of 2x plus 1, the function that we used before. And c is here, c is 1, and the purported limit L is 3, this one. Here where we can put entries for epsilon and delta. So the doubter will adjust this value, and the convincer will also adjust this delta value in accordance to that changes happened in the epsilon. So for the meantime, epsilon is set to 1.4, so that is how far away it is, the function is from the purported limit L. While delta is set to zero point 0.4, so notice that when we adjust delta, if this is zero point 0.6, then this set of points are well inside the epsilon restriction, so that is fine. So you can, if you adjust further, then there is a problem. Some points are going outside the epsilon restriction, meaning you cannot go beyond like 1. I think when we crossed 1, then points are already outside. So 0.7 is okay. So the challenger now will try to adjust the epsilon. So when epsilon is 1.5, delta, which is zero point 0.7, is fine. But if we make it smaller, 1.1 epsilon, zero point 0.7 will not work. So we have to adjust it. The convincer will have to decrease this value. When decreased to zero point 0.5, then still fine. Points are inside the epsilon restriction. So the convincer is still able to find delta. How about when epsilon is zero point 0.9? Will the convincer be able to find a delta? Yes, it does. We have zero point 0.3 as a response to zero point 0.9 epsilon. When epsilon is zero point 0.6, then zero point 0.3 will not work. That point is not inside, but 0.25 does. So zero point 0.2 delta response is 0.05, still inside, and so on and so forth. So I think you're getting the idea that um, to claim or to prove that the function has really a limit L as x approaches the C, then the convincer has to always come up with a delta value in response to that epsilon requirement. So if the convincer is always able to do that, the mission is accomplished. But if at least one epsilon is found so that the convincer has no delta response, then that's the time that we say that L is not the limit of the function. The purported limit number L is not the limit of that function as x approaches C. Okay, so illustration 3 show that the limit of x squared minus x as x approaches 2 is equal to 2. Justification. So again, we need to identify the given f of x, the c, and the l. Then we proceed with the usual routine. Let epsilon be greater than 0 We want to find delta such that if the distance from x to c is in between 0 and delta, then the distance between f of x and L is less than epsilon. This is what we want to accomplish. Just like before, we want to manipulate the conclusion part, this one, of this conditional statement to extract the absolute value of x minus c to come to elicit this expression, because that is where we will be able to find the value of delta. And there we, let us see. So we manipulate the conditional the part, the conclusion part of the conditional statement. We can factor it. Property of absolute value, we can write it this way: a product of two expression inside absolute value. And there we have it. We have elicited the expression, the x minus 2. That one. That's what we needed. But there's still a problem. Even though we were able to extract this expression, there is another variable expression, the x plus 1, that may affect our assignment of delta value. So this is different from the example number 2, since this one is not constant, unlike this one. For otherwise, we could just define delta as epsilon divided by that constant. But as we said, this one is different. So what should we do now? Well, we can make this expression a constant. But how? Well, remember that the very purpose of finding delta is to take x sufficiently close to c, so that the epsilon requirement is always met. In other words, we are looking for a domain from which x can take its value. So for the meantime, we can restrict the absolute uh, value of x minus 2 by a fixed number, say 1. So there are some things to consider when nominating this number, like continuity, but the function at hand happened to have no issue on that aspect. So we're good to go. If the actual delta, meaning delta value that works, is bigger than 1, then it is good. If the actual delta is smaller, then we have a problem. But we also have a solution to that. You will see later how we can resolve this. So if the absolute value of x minus 2 is less than 1, then x is any number in between 1 and 3. In effect, the expression absolute value of x plus 1 is less than 4 on that interval. This means that in the interval from 1 to 3, the absolute value of x plus 1 times the absolute value of x minus 2 is less than 4 times the absolute value of x minus 2. So we are able to um, frame this variable expression x plus 1. And we found that this is less than 4 when x minus 2 is restricted by this nominated delta value. I think this is now becoming clear what delta can be based on this expression, but not so fast. Remember that this is only true in the assumption that the absolute value of x minus 2 is less than 1. Under that assumption, thus we have to account for that. Hence, our definition of delta would be Accounting for this additional assumption, the delta would be not only epsilon over 4 but the minimum between epsilon over 4 and that introduced delta or supposed delta. So this ensures that the absolute value of f of x minus L is less than the formal proof would look like this. In essence, the process of justifying that L is the limit of f of x at C centers on finding the appropriate value of delta with respect to epsilon. There is really no prescribed procedure for this, but for students who are required to perform this task, you can follow these guidelines. So I decided to make use of another problem for better illustration. So the guidelines in justifying or finding the delta from the given epsilon, step 1 is to identify f of x, c and l. Then step 2, form the absolute value of f of x minus l and extract the absolute value of x minus c from that. In so doing, this will elicit uh, a factor which I call g of x, a variable expression like this one. So I call it the g of x. Step 3, um, find an upper bound for the absolute value of g of x by introducing a temporary restriction to the absolute value of x minus c. So this can be any number, but there are some restrictions to choosing. So maybe you could use a very small number. So an upper bound for the absolute value of g of x can be identified as using this additional restriction. You can find the upper bound for that factor that came out. So for example, in this case, g of x will be found to be 1 over 6. Step 4, define delta as the minimum between the introduced restriction, that one, in number 3, and epsilon over the computed upper bound, that one. These guidelines may not work for every given problem, but should work on a majority of them. Okay. Remarks. First, the value of delta, which depends on the given epsilon, is not unique. So different students may find different delta value on the same epsilon. Of course, epsilon is always epsilon. So once you found the delta value that works, any number less than that also works. There are various ways to obtain the conclusion. So the absolute value of f of x minus L is less than epsilon from from the assumption that absolute value of x minus c is in between 0 and delta. So there are many ways to obtain this. Next, introducing temporary restriction to the absolute value of x minus c is done in case-to-case basis. Sometimes this part is not required.